Okay, hey everyone. Thank you for coming. We're lucky to have Nikhil Garg today with us for the DSI seminar. Nikhil is joining us from Cornell Tech, where he is an assistant professor in operations research and information engineering. His research focuses on applying algorithms, data science, mechanism design to the study of the democracy, markets, and societal systems at large, which we'll be hearing a little bit about today. He received his PhD from Stanford, and he spent time helping numerous companies, where he's most recently been the principal data scientist at PredictWise, which provides election analytics for political campaigns. With that, I'll hand the mic over to Nikhil. Thank you for joining us.
Okay, thanks, Keyon. Yeah, and thanks everyone for having me and sort of coming to this talk. So today I'm going to talk about the research direction that I've been most excited about recently. The paper is not online yet, so if you have any questions or thoughts, just feel free to email me. My email is up here, and this is, I think, the first time I'm presenting this work to an academic audience, so definitely happy for any feedback or thoughts. Okay, so the work's entitled Equity in Resident Crowdsourcing, Measuring Underreporting Without Ground Truth Data. This is joint with my PhD student, Zhi Liu, who's also at Cornell Operations Research. And this work wouldn't have been possible without the Urban Tech Hub at Cornell Tech, which does sort of has a lot of interactions with New York City agencies, and then through them sort of got in touch with the New York City Department of Parks and Recreation, which, as you'll see, is sort of really helped us out in this work, both in sharing data and providing internal insight and thoughts. Okay, so maybe now is a good time for the poll, Alexis. So maybe just to test interaction, we'll do a very quick audience poll, which is, have you ever made a 311 report?
Okay, 17 people have, I'll let it run for another 30 seconds.
Yeah. So maybe while people are answering that, I can sort of maybe quickly, actually, so while people are answering that, I do want to make this as interactive as possible. The way my screen's set up is I can see the Q&A, I can see the chat. So please feel free to just drop in questions and then I'm happy to sort of respond anytime. I know it can be a little rough and sort of in these webinar type Zooms to have interaction, but would love as much interaction as possible. Oops. Okay, so maybe we can end the poll. And how do we see the results? Yeah, let's just show the results now.
Hang on, I can share the result. Can you see it on your end?
I can't, no.
Let me see. Can you see it now?
Yes, okay, perfect. Okay, so so about half of you don't know what a 311 system is. Most of the rest of you know what it is, but haven't made a report, and we just have a handful of people who have made a report before. Okay, so great. So let me explain what 311 is. So many cities, New York City included, have a phone number that you can call to complain to the local government. And so the way to think about this is you call 911 to complain to the government, or sorry, you call 911 if you need an emergency personnel to show up to your doorstep right now. You call 311 to complain to the government about a problem that hopefully will be fixed in the next few weeks or something, but you don't necessarily need someone to do, like right now or in the next 10 minutes. And so maybe the canonical example for these reports is potholes, but you also have bed bugs, trees that are diseased, about to fall down in the power line, or so on. And sort of as expected, I think sort of a lot of you either don't know what this is or haven't used it before, but these systems really are huge. The New York City government received, so the New York City system received about 2.7 million requests last year. And these are really the primary way that a lot of sort of government operates and learns about problems. So as an example, we're going to work today with street trees in New York City. And so these are trees that are on roadways or streets, and not counting like trees in parks or like Central Park, except I think they potentially count trees that are on the sidewalks and roads in the parks. It's a weird definition, but anyway, so New York has about 700,000 of these. And it's, you know, they have a small parks department that has a tiny budget. That's about 0.5%, 0.5% of the New York City budget. And, you know, the parks department doesn't possibly have the personnel to surveil all of these trees in real time. And so the primary way they learn about problems is through 311 reports. And so the general pipeline is about as follows. You know, an incident happens. And so, you know, maybe the tree is diseased, or, you know, a branch falls down on a roadway, or, you know, the tree starts growing on a sidewalk and, like, you know, cracking the sidewalk. And at some point, somebody might notice the incident and then decide to report it to the 311 system. So for example, the forestry subunit responsible for street trees in the New York City Department of Parks and Recreation receives between 70 to 100,000 reports a year. About half of these reports, someone in the agency is actually going to like physically walk to the location and inspect the tree that someone made the report about. And you know, they're going to write up a report about whether they found the problem and so on. And about half of these inspections are going to result in actual work getting done. So they're going to call sort of a crew to come in and, for example, put sort of, if it's some disease or pest, to try to treat the tree for that. If it's, you know, some like tree falling down, to remove the tree, or to prune the tree, or to remove branches or so on. And so this is probably, it's not an exaggeration to say that these 311 systems are probably the largest crowdsourcing to operations pipelines that we have, certainly that we have in government. And the high-level research agenda that I'm going down right now is how can we audit and improve this process's efficiency and equity. And so today's work is just going to talk about the first part of this pipeline, is how do we understand reporting behavior? So an incident happens, how long does it take, if ever, for a report to be generated? And why is this important? If we have disparities in who reports problems, then there's going to be disparities in what work gets done. So if, you know, if rich or more educated neighborhoods are submitting far more problems conditional on the same incidents happening, then they're going to get better government services, because they're sort of, you know, the parks department can't do many work orders unless they see the, unless like, you know, a report comes in. And so sort of what I'm going to talk about today is trying to understand this first arrow, from the incident to the report pipeline. Okay. Now, there's a really nasty statistical challenge in trying to do this. In particular, how can we distinguish between underreporting and the neighborhood truly having fewer problems? So, like, by definition, we don't observe data on missing reports, right? The entire point of these systems is that the Parks Department can't know about problems that don't exist. And so if we don't observe a report, then us as researchers don't observe that that problem happened. And so maybe another way to say that, if a tree falls down in the forest and no one reports it, the city doesn't really know about it. Okay, and so the methodological challenge that I'm going to talk about for maybe about half or more than half of the talk is to try to overcome this missing data issue. And I just want to briefly mention one approach, which is and I'll talk about this more later. This is the primary approach used in prior work, and that you might think is fairly reasonable. I mean, it is fairly reasonable, and sort of it might be the first thing that you want to go to, which is, okay, you don't have ground truth data on all possible report on all possible incidents that happen, but maybe you have ground truth data on a bunch of them. So, you know, how, like, find some way to estimate how many incidents of each type, you know, like something that's actually a hazard, like a tree, like a, you know, something that fell down on a roadway, or like root issues, tree pruning requests. How much of each of these types of incidents do you expect to see in each neighborhood? And there's a few ways one could go about trying to construct this ground truth. So, for example, you can go out and physically walk the streets and try to get a snapshot, uncensored view of the problems that are actually there. And to some extent, the New York sort of Parks Department does do this. I think it's, I forget the number, I think it's about 5% of trees they try to annually go about and do inspections on. And this is, it's often not purely random 5%, it's often in sort of in communication with the community boards in New York to try to figure out which trees that they want to actively inspect. So you can, you know, try to just like go out and do this expensive data collection. Or you could try to construct proxy measures, right? You can try to, you know, I showed you that slide, that picture on the first slide of just each street tree in New York. So you can just look at the number of trees in each neighborhood. You can look at their size, you can look at their species, and you can just try to come up with some estimate of how many problems you would expect to see. And I'll talk about why this might be challenged. Sort of, I don't want to talk about this too much, but sort of one could imagine that this is maybe not precise enough. That one could imagine that for the actual operational things of, you know, exactly of each type, constructing these proxy measures might be an expensive or hard thing to do. And so the research question that we have in this work is, can we measure underreporting? Or more generally, can we measure differential reporting for different types of incidents or different neighborhoods without this ground truth data? The key idea is we leverage the key idea from this long line of work in empirical Bayes called the missing species, from the missing species literature, which is we can leverage the rate of duplicate reports made about the same incident to identify the reporting rate as distinct from the incident occurrence rate. So maybe another way to say this is the first report about an incident tells us the incident exists, and the remaining reports tells us what the reporting rate is for that incident. There's like sort of a few other subtleties that you have to take care of to actually sort of adapt this idea. And I'll talk about that in quite a bit detail in a little bit. But yeah, so the first thing that we do in the paper is we develop the statistical method in order to be able to do this, to be able to measure underreporting or delays in reporting. Then we apply the method to audit reporting behavior in New York on street tree incidents over 3 years. And then ongoing work is we're actively working with the Parks Department to help change the operations in order to improve the efficiency and equity of the entire pipeline. And I'll talk a little bit about this research agenda near the end. And maybe I just want to give sort of a quick high-level theme, especially for the students in the audience, which is I think we're in an age that we can do a lot of sort of work, especially for governments and nonprofits, using data that wasn't available 10 years ago. Sort of, especially with like in New York City, with the New York City Open Data Law, you can leverage very precise, real-time, often sort of completely open administrative data to audit and design, like to audit systems and to design to help improve operational processes in a way that wasn't possible 5 or 10 years ago. Maybe if especially the students in the audience get one thing out of my talk, I would just Google New York City open data right now to, and then sort of just look at like the large variety of data sets that you have available to sort of do all sorts of analyses. And especially for like, you know, those interested in like algorithmic fairness and those type of issues, I think this is a great way to like, you know, go beyond everyone using the same like 5 or 6 data sets for those types of papers. Okay, so that's just a small side plug, but let me get back to what we actually do. Okay. Actually, before I do that, I just want to encourage people to type in any questions that they have either in the chat or in the Q&A. I do see that on my screen, so I'm happy to sort of like answer questions in real time. I know the webinar format kind of makes questions hard. Okay, so feel free to type in questions, but I'm going to move on. Okay, so this work sits at the intersection of a few different literatures. Perhaps the most obvious one is there's a large literature on these type of 311 systems, often called coproduction systems, often in government or sort of administrative departments. And for example, there's sort of a professor at NYU, Constantine Contacosta, who does a lot of work on these type of systems. Or a few people in sort of the operations or sort of business schools have thought about operational transparency and like how much people know about the 311 system and like that work is getting done influences reporting behavior. So this literature primarily asks, is reporting behavior similar across areas? And that's the same question that we have here today. And they primarily do that using proxy ground truth data, which sort of, as I'm going to go in a little bit, might not be as precise as we would want for more operational tasks. And then the second thing this literature asks is the city Responding to reports equitably? Is given the reports, are they prioritizing some neighborhoods over the other? We don't touch on that in this work yet. More methodologically, this work touches quite a bit on, as I mentioned earlier, on sort of this few lines of work on how can we estimate the prevalence of a species, so like an animal species in an area. And in the missing species literature, this sort of boils down to how many species exist in this area that you haven't seen yet. Or in the ecology literature, it talks about how many of given species are there. And what we do in this work is we primarily leverage insights from this first question of this missing species literature. And we adopt some of these ideas, especially also in the ecology literature, to look at similar questions. But we think our approach really is unique in using administrative data to sort of identify exposure time, or like how much you're looking for something versus like how much something is there. So sort of we hope that the tools that we develop can be now applied to especially the second question in the ecology literature as well. And then lastly, what we end up doing is showing how if you look at the problem in the right way, you can reduce it to a quite standard Poisson rate estimation task, at which point you can leverage a large both literature and practice as well as theoretical literature on how to estimate Poisson rates effectively. So for example, the empirical side, which I'll touch on or really go into at the end, just uses off-the-shelf Poisson rate estimation methods implemented in STAN. Okay. Any thoughts or questions so far? Please feel to type them into the chat. I don't see anything yet, so I'll just move on for now. Oops. Okay, so let's just drill down on the data generating process. I'm going to have a bunch of incidents where each incident is going to have a type theta that you can think about the type as encoding geography or incident characteristics. So like what is it a hazard? Is it a root issue? What's the tree? How big is the tree? How risky is it? So on. And then in incident I, so a given incident is going to occur according to some process big lambda of theta. And it's going to occur at some time that we don't observe. Okay, so the incident occurs at some unobserved time according to some process that we don't really know about. And then people are going to report that incident according to a Poisson process with rate lambda of theta. And I just want to emphasize here is I wrote this as just a singular rate, but you can think, I'm not imposing at the moment any assumptions on whether it's homogeneous Poisson process or, it can be varying as a function of time, as a function of the sample path, so on. But just it's going to occur according to some process. Okay. And so, for example, at some time after the incident occurs, we're going to get the first report. And the city, through, of course, the 311 system and us as researchers, observe this first report. And that's when we know that the incident exists. And then maybe, there's going to be a second report and a third report and so on. At some point, either before the last report or after the last report or so on, at some point, the Parks Department might inspect the problem. So they might physically send out an inspector to look at it. And this is going to be observed in the data, the time of when they did it, as well as the outcome of the inspection. And then we're going to say at some time, the incident is going to die. By die, I mean it's either fixed by the agency, and if it's fixed by the agency, then that's going to be in the data. But it could also be fixed by someone else. So there's a whole bunch of civic groups that adopt a street, adopt a park, or just like someone goes in, like a random resident or a random person goes in and fixes the issue, and that's going to be unobserved. So we're going to say that the death time, for simplicity, is unobserved. And after the death, we're not going to see any more reports. And so another way to think about it is between the incident time and incident death, we're going to observe, which are both unobserved, we're going to observe reports that occur according to a Poisson process with the rate lambda, little lambda of theta. And then the research question is, how does this reporting rate depend on the type? And so, why does this matter? If I have a slower reporting rate, so if reports come in more slowly, then I'm going to have a bigger delay between between the incident actually occurring and the city knowing about it. And if the city doesn't know about it, then they, of course, can't inspect and fix the issue. And so we're going to have, a lower reporting rate means delays in inspections and fixing the issue. And, if the incident dies, if it gets washed away or people just get used to it or so on, some incidents may just never be reported if they die before the first report. And so the Parks Department might just never know about it. And so what we're interested in is, how does this reporting rate, depend on the type? And what I want to emphasize is, it's okay, type dependence is not is not completely a bad thing. So in an ideal setting, more dangerous incidents are going to be reported more quickly, right? So if something is really, if a tree has fallen down on a roadway or is about to fall down, you really want that reported as soon as possible. Whereas if something is less dangerous, it's not a big deal if that's reported 3 weeks later. But the concern is that some neighborhoods are going to use the 311 system less than other neighborhoods do. And so they're going to have lower reporting rates for the same types of incidents. And that's where downstream disparities might occur in who's getting government services and how effectively. Okay, so our goal is to identify this reporting rate little of lambda. And the challenge is how can we distinguish that between the incident rate, which is how many incidents of that type, or how quickly incidents of that type are happening, versus reporting rates, which is how quickly incidents of that type are being reported conditional on happening. And so maybe to illustrate the difficulty in distinguish these things let's talk about maybe the most naive method one can think of to try to get at reporting rates. So what one could do is one can simply count the number of unique incidents that are reported for each type within some time window. So a month or a year or whatever. And then simply compare these two numbers for two different types. So simply compare how many hazards were reported on the Upper East Side versus how many hazards were reported on the Upper West Side. And if one is higher than the other, then maybe the little lambda, the reporting rate for that neighborhood, is higher than the other. Now, this only works if the incident rates are identical, right? So if problems are truly occurring at the same rate on the Upper East Side as the Upper West Side. And even under that assumption, this naive method doesn't tell us about delays, doesn't tell us how long it took for that incident to be reported. All it tells us is comparatively how many got reported and unreported. And previous works in the 311 administrative literature either sort of do exactly this method by ignoring this issue. So they implicitly assume that incident rates are identical, or they find proxies for the incident rate. So they say, you know, the Upper East Side has, 10,000 trees versus 15,000 trees. And so I expect to see about 1.5 times more incidents of each type in the latter neighborhood, right? And then compare these normalized numbers to try to get at reporting rate. And how can you do this? So you can look at the number of trees, you can look at their size, species, you can look at the active inspections that I talked about. In ecology literature, you can assume that for some reference type, so in the ecology literature, they say for like some type of species, these two parts of the forest should have similar of those species, and then use those species to normalize sort of how much you searched in each of those parts. Okay, but we don't want to use this method because even if this normalization worked, it doesn't tell us about delays. And what we really want to understand, especially for operational reasons, is understanding delays and really precisely how it affects on the type data in a way that might you might need more detail than proxies. Okay, so the first insight is that we don't want to just look at the counts. We don't want to look at the count of the number of unique incidents, but we want to also look at how often we observe reports about each of those observed incidents. And so maybe as intuition here, suppose we actually observed for the incidents that occurred, suppose we actually observed when they happened and when they quote unquote died. Then according to the assumptions that I gave, the number of reports in that time span is just a Poisson process with rate lambda theta that might differ over time, along with exposure time or time duration, the length of t. And that's a problem that we know how to solve. This is, thousands of papers on how to do Poisson rate estimation. And so if we have this time interval, then we can calculate the rate estimation using these number of duplicate reports, and then we can use that to understand this delay. Now, the problem, of course, is that we don't observe this interval. We don't, even for incidents that we know occurred, even for incidents where an inspector physically went out there and looked at the incident, they don't know when the incident happened. All they know is when the incident was first reported. And so we can't actually use that method. Rather, we need to find an interval within which the reporting rates are Poisson. And so we have the following theorem. Now, this is not a theorem that's like, super hard to prove or anything. It's more of a translational theorem to understand exactly the conditions that we need that will help us construct this interval in practice. So the following are necessary and sufficient. First, we need this interval to, of course, be between the birth time and and the death time. So we need to start looking for reports after the incident happened. because reports will definitely not happen before the incident happens, and before the incident dies, because reports are not going to happen after that. And we also need the interval to be what's called a stopping time, which means that they can depend on the past, but they can't depend on the future. So the end of the interval, for example, can depend on how many reports happened up to that point, but it can't depend on the future. And conditional on the type theta, it needs to be independent of the reporting rate lambda. And so, especially for those who haven't seen Poisson processes in detail before, let me just try to translate what this means for our setting by some naive ways that one could try to construct this interval, and then maybe some less naive ways that actually work. Okay, so the first observation is that the best choice for the start of the interval, sort of the unambiguously best choice for the start of the interval, is the time of the first report. Because at the time of the first report, we know that the incident exists. So we know that, of course, it happens after the incident occurs. And this is a stopping time, right? It doesn't depend on the time of the second report or the third report. All it depends on is the first report happened at that time. Okay, what about the end of the interval? Now, naively, one might want to just fix some duration, to just say that I'm going to look at some time. So what I'm going to do is I'm going to look at how many reports happened after the first report, but within 3 weeks of the first report. So a fixed duration length. Now, the problem is that incidents have very different alive durations. So some incidents are inspected by the, and so I'll show what this actual plot is in a little bit and discuss it in detail in a little bit. But for now, just think about this as, this is how much time it took for the first report for the incident to be inspected. And so some incidents are inspected within a day. Some incidents aren't inspected until 3 months later. And then there's actually a quite long tail that I cut off. And so if we need this end interval length to be before the dead time, we actually would need it to be within a day or something. We could only look at how many reports happened that first day after the first report, because otherwise the end time is going to be after sort of most reports got fixed, and you would be systematically sort of underestimating the reporting rate. Okay, so we can't use a fixed time. Okay, maybe attempt number 2 is we can look at the time of the last report. So we can say that, at some point I got a report, and at some point I got the last report, and then let me just simply think about how many reports happened in between the first and last report. The problem is this is subtly using information about the future. And in particular, it's using the fact that I didn't receive any more reports. And so concretely, this is estimating our bias of the reporting rates downwards, because we're systematically excluding times in which the incident hadn't died, but there were no reports, because sort of that's the definition of this in the data. And so maybe another way to see it is if most incidents didn't get a second report after the first report, then the interval would just be this length 0. I would say, oh, the incident died immediately. And so I would be ignoring a large amount of time in which the incident still hadn't been fixed, but there were no more reports. Okay, so those are our 2 attempts that don't work. So what does work, or what approximately works? I'm going to claim that the minimum of some fixed length t, we used 100 in the reports, in the data I'm going to share, in the results I share with you, but this could also be results don't change if you use 30 or 300 or so on. And the claim is that we're going to use, if we can use the minimum of this fixed time and the time that was inspected by the Parks Department. And so by looking at this inspection time, it fixes the problem of this first duration length. I mean, it fixes the problem of attempt number one, which is for things that got inspected within a day, we're not looking at 30 days, we're just looking at 1 day interval. But for things that got inspected 2 months later, we're looking at the entire 2-month period. And what I want to emphasize here is that it's okay that this inspection depends on how many reports happened. It's actually okay that this is like, for example, that the Parks Department inspects something faster if there were 2 or 3 or 4 reports in like very quickly. That's what it means for this inspection time to be a stopping time. As long as the inspection doesn't depend on the future. So unless the Parks Department as time travelers, it won't. And maybe the higher level insight is which we used here, which might be able to be used in the ecology or like another literature and other settings, is that we can use administrative data to sort of carefully calculate an incident level exposure time or Poisson interval in maybe ways that we were making assumptions or distributional assumptions before in that literature. Okay, so there is a question in the chat. Let me just read it and then. Okay, so the question is, isn't this downward bias also true because we're systematically ignoring sort of the time between the incident occurring and the first report? And it would be if we were using this first report. So if I was I constructed this interval A to B, and if I counted the first report as something as a report in that interval, then yes, I would be systematically ignoring sort of this time. But it turns out that if I ignore this first report, if I just arbitrarily say I'm going to start looking at the time of the first report, but not count the first report, it turns out it doesn't end up downward biasing you. Okay. If there's any other questions in the chat, sort of feel free to drop them. Otherwise, I'm going to move on. Okay, so what's the summary of the method? For each incident, just construct an interval, sort of as I said above, and count the number of reports inside that interval, but not counting the endpoints of the interval. Then the number of reports for that incident is distributed according to a Poisson process inside that interval. So for example, if we're assuming an homogeneous Poisson process where the rate isn't changing, then the number of reports is distributed according to a Poisson process with rate lambda of theta times the length of the interval. But we don't have to assume a Poisson process. We can the same result holds for any assumption here. So for example, and I'll show you why in a little bit with the data, you can do what's called, we end up doing what's called a zero inflated Poisson, which is essentially saying that for a subset of the incidents, maybe we don't, you flip a coin and no matter what, you're not going to observe a second report after this first report. So, and that happens with probability 1 minus alpha. But if the coin flips the other way and you do continue seeing reports, then it's going to happen according to an homogeneous Poisson process with rate lambda of theta. And maybe a realistic data generating process that generates this is, some things are some complaints are very personal, some person who lives in a house is requesting that the Parks Department prunes the tree in front of their house because it's overgrowing into their yard or something like that. And so you wouldn't expect to see someone who doesn't live there maybe worry about that. But these are just two things that we ended up using. What's nice about the method is you can use fairly any general process that you care about within this time period. And then maybe the last thing I want to talk about the process is even this isn't practical yet because the type data might be really high dimensional, right? So the type data might depend on location characteristics. It might depend on the type of the incident. It might depend on the actual text of like, someone called in and the operator is like typing what the person said, or someone submitted through the app and they themselves typed what they said. So, this type data can be really high dimensional if we care. And so we don't want to do this differently for each type data. And so we end up doing a Poisson regression where we basically say that this type, this reporting rate depends according to a regression where we're actually learning coefficients for each, for each dimension of the type. And so maybe one example of this is we end up doing for when we actually want to understand spatial heterogeneity, we end up using what's called an ICAR, or intrinsic conditional autoregressive spatial model, which is a fancy way of saying that I have, the type data contains an indicator variable for each census tract in New York City. So that's over 2,000 census tracts. But the coefficient for each census tract is drawn with mean of the neighboring census tracts. And so this is sort of borrowing information if in one census tract we got very few incidents, we're going to borrow information from neighboring incidents. And this is turns out this is very efficient to implement in STAN, to do a Bayesian Poisson regression in STAN. And sort of this paper, Morris et al., Andrew Gelman is one of the et als hidden here, walks through exactly how to implement this and ends up being fairly easy. And that's maybe a side note that I want to emphasize here is what's nice about our method is we can, once we figure out exactly the right interval to use, actually deploying this in the data can just leverage a whole bunch of off-the-shelf Poisson rate estimation. Okay, so we end up doing this. And then we're going to apply this to understand reporting behavior in the New York City 311 data. So the data we use is mostly public. So actually, like y'all can Google right now 311 reports in open New York City open data. You can download I think it's like over 30 million reports made to the city of New York since 2010. We use a subset of the public data that's only for forestry service requests. And then we talked to the Parks Department and they augmented our data with internal data on sort of providing more data on the inspections that they did, the work orders, and they also provided anonymized caller information. So who's actually the person who called about this incident. We ended up using about 220,000 service requests over a 3-year period in June 2017 to June 2020. And this just overlapped. This is just the period that they gave us public data for. The private data you can download actually even the request that happened yesterday. That gets updated on a daily basis. Of these, about 115,000 requests correspond to things that were inspected, corresponding to about 99,000 unique incidents. And for each incident, we observe a bunch of covariates that we're going to put in the type for that incident. So things like location, we convert latitude, longitude to the census tract. Things like the characteristics as reported by the caller. So category, is it a hazard? Is it a sidewalk damage? So on. We also observe the inspector report. So when the inspector went out, if the inspector went out and did it, looked at it, what risk rating did they assign to it? What precondition did they assign to it? Okay, so now I have the data, I have the method, we can just run those regressions on the data and show you the results. Before I do that, I just want to briefly mention 2 potential sources of statistical bias that might affect the results, but we don't believe actually do. And these are just because of quirks of the data set. Or the first one is, I think, more fundamental. The second one is a quirk of the data set. So the first one is in 311 systems, reports might not be independent. So for those of you familiar with Poisson processes, the big assumption is that reports are memoryless, that they sort of one report occurring doesn't affect the rate at which the next report, or doesn't affect sort of the actual time that we're going to get the next report in. Now that obviously doesn't hold if the same person is like, every day, every morning, they're like, they haven't fixed my problem yet, I'm going to call and complain again. And so we need to filter out repeat callers. This is where the fact that we were in communication with the Parks Department really helps, is that we obtain hashed caller information. So don't have to worry about privacy. They hashed everything before they gave it to us. They gave us first name, last name, email, and phone number. And so all we did was we filtered out repeat callers. We also, now, of course, not everyone is going to give their first last name email. They might give wrong ones or so on. So we also constructed a more conservative data set, or the more conservative one doesn't take care of incorrect, like someone gives the wrong name, but does filter out people who didn't leave their information, where we also sort of checked everything in the more conservative data set in which we just filtered out everyone who didn't leave information. And the results are basically the same. Okay, so this potential source of bias doesn't really matter. The second most more informative one, or more potentially destructive one, is a quirk of how the Parks Department labels duplicates, in which they only label duplicates for in their actual system for incidents that they inspected. The inspector sort of, or the potential inspector, has an idea of duplicates even for things that they don't inspect, because that helps them decide what they inspect, but they don't actually end up marking that in their database. And so this would lead to bias if, even conditional on the type theta, the inspection decision is dependent on the reporting rate. I'm happy to talk about this offline, but for a few reasons, we believe that this bias is small if it exists in the data set. And it's especially small heterogeneously, because what we actually care about is not just the bias, but does it affect, Upper East Side as differently from the Upper West Side. Okay, so some very quick summary statistics. I know I only have 10 minutes left, so I'm gonna do this fairly quickly. So what I have here is the length of the observation interval that I'm gonna look at the incident level. And so this is effectively the same plot that I showed you earlier, where this is showing, but now I'm also showing you the censoring at 100, where this is the time in between the first report and the time that the agency inspected the report, or the minimum of that in 100 days. And so you see a bunch of things got inspected almost immediately within a few days, but there's a long tail. So notice this is on the log scale, but this is on the 10 to the third. So there's a long tail that the Parks Department's not super happy about, that it might take them months to inspect something. And then this is the plot for the number of duplicate reports, where this is how many reports I see after the first incident within this observation interval. And what's nice is you can see that this is mostly Poisson. We see more zeros than one would expect for a Poisson distribution. So for a Poisson distribution, we would expect, because this is on a log scale, we would expect that this linearly goes down. And that's basically what we get, except we see more zeros than we would expect otherwise. And that's what motivated us to do the zero inflated Poisson. And then maybe the last thing you're worried about is, at least the estimation that I showed you, we don't do anything where the rate is changing over time. So we don't like say that, 3 weeks after an incident has passed, we're going to report at a lower rate than after the incident just happened. And you might be worried about that, but this plot is showing you that it turns out, besides the zero inflation, it mostly does look Poisson with an homogeneous rate. And so what this plot is showing you is, so for example, this first line that ends at 1 is showing you 4 incidents that had at least one duplicate. How long did it take for that first duplicate to happen? And it took about 6 or 7 days. And then this green line is showing you 4 incidents that had at least 2 duplicates. How long did it take for the first duplicate? How long did it take for the second duplicate? And then that's about 10 days. And what's interesting is each of these lines are linear. Sorry, lines are of course always linear. Each of these plots are approximately linear, where you see a few kinks, but really it's it's approximately linear. So the reporting rate's not really going down on average. But what is happening is 4 incidents that tend to have higher number of duplicates, even the first incident is being reported faster. Yeah, and so this is surprisingly homogeneous, which is why we just went with homogeneous estimation. Okay, so with that, let's go to the actual results. The first set of results is the good news, which is for the most part, reporting rates are fairly efficient in the sense that we see higher reporting rates for more urgent incidents. So for something that the reporter marked as a hazard versus something that they just marked as like regular tree damage or a request to remove a tree or so on, we see much higher reporting rates. And I'll contextualize this in a little bit. So we see between 3 to 7 times higher reporting rates for hazards than we see for other things. If we look at the things that the Parks Department marked it as, so if the inspector marked something as more risky, we observe a higher reporting rate. Or if the Parks Department inspector marked it as a tree in poor or critical condition versus a tree that's in excellent or good condition or already dead, we see a higher reporting rate. So this is all good news for the Parks Department. Maybe this root sewer sidewalk issue is not great news because they do care about these issues, but this is mostly good news that we see higher reporting rates for things that are more hazardous. On the other hand, reporting rates also vary quite a bit by neighborhood, even conditional on incident characteristics. So even if the regression also has those incident characteristics, we see quite a lot of sort of high absolute value coefficients for individual census tracts. So the difference in reporting rate between the census tract, and so this is using that ICAR spatial regression that I talked about earlier. The difference in reporting rates between, in Manhattan versus parts of Queens and Brooklyn is, up to 3 or 4 times the reporting rate in some census tract. And so we see a lot of spatial heterogeneity that the Parks Department's not super happy about. So I showed them this plot and they were like, well, can we get a list of the census tracts with low reporting rates so we can try to think about interventions like sending out advertisements or things like that about the 311 system. And you can also see that these census tracts, these rates are going to correlate with, you can measure this in a few ways, but they correlate with socioeconomic characteristics. So maybe the most obvious one is we see higher reporting rates in more dense neighborhoods, right? So the higher the population density, the more we see, but then we also see correlations with education, ethnicity, wealth, all the demographic correlations that you wouldn't want to see. And then I just want to end this with contextualizing these reporting rates. So suppose I had an incident that was a hazard. So reporter marked as a hazard. The inspector marked it as something in poor condition, and that something was high risk. This is something we need to fix immediately. In Manhattan, you would expect to see an average reporting delay about 2 days, whereas in Queens, you would see an average reporting delay about 4.5 days. For something that the reporter marked as tree damage and that the inspector marked as in poor condition, you would see a delay of about 12.5 days between the incident happening and it being first reported, and then up to 27 days in Queens. And then for something that's a root, sewer, or sidewalk issue, and for a tree in fair condition, you would expect to see about 100 and 200 day delay on average between the incident happening and it first being reported to the Parks Department. So we definitely have huge heterogeneity, both across locations and across types of incidents. And then I just want to end in 1 minute with sort of giving an advertisement to ongoing work and for sort of hunting for partners, which is what we're now thinking about is, okay, great, we've thought about auditing the current system. How can we actually help 311 agencies who respond to 311 reports respond more efficiently and equitably? And then the other one is essentially the same methodological tools can be used in a whole bunch of other applications. Now, of course, other city agencies that respond to 311 outside the Parks Department, but also we think they can be used fairly off the shelf for, like, for example, for software bug reporting. And so if you're someone with access to these sort of applications, please shoot me an email, come talk to me. Happy to sort of work together. And with that, I'll thank you for having me. We're happy to have questions. And the last minute I have, I'll put my email out again.
Thank you, Nikhil. That was incredibly interesting. So yeah, people feel free to ask questions in the chat while people are typing or asking questions. I have a question or two. You mentioned at the beginning that there are these like proxy methods that you don't deal with to measure estimate incident rates. I was wondering, would it be possible to validate your rate estimations with these proxies?
Yeah, that's a great question. So we don't do that yet. We definitely have some data. So like from New York City Open Data, you can download the tree sense. So you can download how many trees there are in each neighborhood. The Parks Department also gave us the results of their active inspection. So we can certainly construct reasonable proxies. And I think that's a great step for validating the data. We haven't done it yet. What we have done is we've shown that the naive method doesn't work very well. So if you just regress the count of like the number of incidents per area, and you regress that with our spatial coefficients, you actually get sort of no correlation or even a slight negative relationship. And so we can validate the naive method doesn't work. We haven't really spent the time doing the proxy method yet.
Cool. Yeah, I was also wondering how you chose this, maybe you mentioned this and I just how you chose this duration length T for the stopping time. Was it just sort of, looking at the histogram, or were there some, were there some other ways? I said we also have a question. Maybe you can answer I don't know if this answer's quick, you can choose.
Yeah, so I mean, the results can definitely, and so the results definitely do, or in theory could depend on that time T. And so, yeah, I mean, it was sort of just looking at the histogram, but then we tried out different things. Like I think in the appendix of the paper, which hopefully will be online soon, we tried out T equals 30, we tried out T equals 200, and like the results don't really change.
Cool.
Like maybe the confidence intervals get a bit wider for 30 because they're just less data, but like the estimates themselves, like the sort of the median estimates don't really change.
Okay, so we have a question that is also about these stopping times. You can read it. I'll also read it out loud. Quick question on how A and B are computed and whether we can disentangle quote unquote reporting and quote unquote inspection rates. So A, the earlier the start time is determined based on the first report, and B is based on when the event is inspected, or a maximum of 100 days. So isn't the computed rate accounting for both report and inspection rates?
Yeah, so that's a good question. So the goal of the method is to disentangle reporting rates and incident rates. I think what the question is getting at is our data does depend on, like, sort of, we only end up doing our method for things that were inspected. And so if the Parks Department is systematically under inspecting in one area, sort of does that affect our results because we see fewer data? So it turns out, and that's mostly because of the quirk of our data, where we end up sort of not seeing the duplicate information except for things that were inspected. That's certainly a potential concern. We don't view that as actually being a big concern in our setting, because sort of for that to be an issue, this inspection time would have to be correlated with the reporting rate, even conditional on the type. So even conditional on that it being a hazard, or what the inspector marked or the size of the tree or all sorts of these things, the inspection decision correlates with the reporting decision. And we don't sort of, talking with the Parks Department, we have reason to believe that that's not actually the case.
Great. We have another question, which is what software was used to analyze the data?
Yeah, so this was all all the Bayesian models were programmed in Stand. So that's, I'm sure some of you at Columbia are very much brainwashed into using Stand. So there's Andrew Gelman's thing on how can we code up large Bayesian models efficiently, sort of run MCMC and things like that. So we did everything through Python, in Stand through Python.
I guess sort of related to this, the software side, was it, how difficult was it getting the data from the city? Was there a lot of back and forth? Was it, was it a smooth experience?
Yeah, so what's nice is that like 90% of this data is public, right? So like the 90% of what we use, you can while I'm talking, you can just download on New York City Open Data Portal. The part that was not public was like some more structured ways of telling us when the inspection happened, what the work order was, and this color information. And there, sort of, I did some hunting, like came up with the idea early, like in August or something, and then was like hunting for partners and talked to Department of Transportation, talked to the Parks Department, talked to others, and like it turns out other researchers at the Urban Tech Hub, which is this really cool thing at Cornell Tech, already had projects they were doing with the Parks Department. And so it was like fairly easy, like it was a fairly painless process for me being added to that collaboration and then them sending me data and like talking to me all the time.
Cool, yeah, that's great. I feel like I have, I've done a few collaborations and these things really depend on, how quick the partner is. So it's good you have a nice experience.
No, but they've been incredible. They've sort of like, I thought getting that caller information would be hard, but like, I emailed them the SQL query on how to hash it. And then like 2 days later, they were like, oh, we ran it. Here's the results. That's
incredible. Yeah, so that said, we're a few minutes over. We should probably wrap up, but thank you for coming, both to the audience and to Nikhil. That was a very interesting talk, and I'm excited to hear, what comes of this.
Okay, great. Thank you. Yeah, thanks for having me. And please feel free to shoot me an email, follow me on Twitter, DM me on Twitter. I don't know. I'm accessible. Okay.